So the content in this video is specific for students doing Physics Paper 1 for AQA in 2022, and that's those who are doing Triple Science. If you want to do Trilogy, I've got another video all about that. Now, in terms of the video, I'm just going to go through a bit of revision on the following topics. We've got energy changes in a system, conservation and dissipation of energy, energy transfers, changes of state in the particle model, and internal energy and energy transfers. So quite a lot about energy here. I'm also going to be going through some of the required practicals you need to know about, and these are Activity 2 and Activity 5. Now, to help you prepare for that, I also have an AQA GCSE revision guide. It's completely free to download over at my website, which is gcsephysicsonline.com. It's got all of the data that you need to remember. It's got some hints and tips and learning checklists for you to go through in your final stage of revision. Also, over at GCSEPhysicsOnline.com, I've got videos about everything. So if there's anything you're not sure about, head over there and you can basically teach yourself over the next couple of days. The other thing, if you are thinking about doing A-level physics next year, that is a great choice, and I have this book that you should buy now. This book here, I wrote it, it's taken ages, and it has questions that start in July, and every day I've got a series of questions for you to work through. And if you start doing the work now, it means in September, when you start your A-level course, you will be much better prepared and it will seem so much easier and straightforward. You can buy this direct from Amazon. It'll arrive in a couple of days' time. So this is the Daily Workout Book 1, and I'm going to have many more books through the whole of A-level physics. I'm going to be really supportive, and I've got loads of videos that you can look at before you start the course. So yeah, let's get started then with some of this final revision. Now, energy is a bit like money, and it can be stored in different places or maybe transferred from one store to the other. And we can also think of it a bit like a liquid that's maybe transferred from different store to different store. Now, there are a number of different stores that we need to consider. So we have kinetic energy, which is due to how quickly things are moving. We've got elastic potential if you maybe deform an object, like you squash it or squeeze it. Gravitational potential is to do with how high you move something. And then we've got thermal, which is the internal energy store, as well as a few others. Now, what we can do is, with energy, we can actually work things out. And if we wanted to work out the kinetic energy, for example, the kinetic energy is equal to a half mv squared, where the v here stands for the speed of the object, and that's measured in meters per second. We should always measure our mass in kilograms, and then this means that the unit for energy is the joule. This energy is equal to a half ke squared, where e is the extension of that object, not how long it is completely, but how much longer it has become. And again, what we do, we measure our extension in meters. K is the spring stiffness, and this is measured in newtons per metre, and once again we measure our energy in joules. Our gravitational potential energy, EP, is equal to mgh. So here again we have our energy in joules, our mass in kilograms. H is the height that something's moved through in metres, and G is what we call the gravitational field strength. And on Earth this has a value of 9.8 newtons per kilogram, but this does depend on where you are in the universe. Some things like the moon, for example, have a much smaller value of their gravitational field strength. When it comes to looking at thermal energy, what we can do is we can change the thermal energy of something by looking at mc delta theta. So here what we have is our theta, that's our temperature, and that's measured in degrees Celsius. We measure our mass in kilograms, and this thing down here, little c, is our specific heat capacity. And this is the amount of energy required to raise the temperature of 1 kilogram of something, of the substance, by 1 degree Celsius. So that means the unit for this are joules per kilogram per degree Celsius. So we have these different stores of energy, but what we can now consider is the different ways that energy is transferred from one store to the other. And there are 4 main transfers that we need to think about. So these are our 4 transfer processes. You've got heating, electrical working, radiation, and this could be things like sound waves, or it could be light waves, and also the rest of the parts of the electromagnetic spectrum. And finally, we have mechanical. Now, it's really important to look at the way that energy is transferred from one store to the other. And what we might consider is at the start of a process, we can maybe consider the energy store. We then need to define a clear end point, and we can consider how the energy is stored at this point. And what we can then do is think about the transfer as well. So these are some of the things we need to think about. If you've got an object projected upwards, maybe it starts as the kinetic energy store and ends up transferred to the gravitational potential store. If you've got a moving object hitting an obstacle, it might end up going from the kinetic store, radiated by sound perhaps, into the thermal store of the surroundings. If you've got something which is accelerating, depending on what provides this force, you might then increase the kinetic energy store. You've got to be familiar with all of these and get used to doing different problems where you might have different energy stores, and that just comes with practice. It's also worth considering how quickly that transfer takes place. And what we can then think about is the idea of power. So power is defined as the rate at which energy is transferred or at which work is done. Now we can say that power is equal to the energy transferred divided by time, and the word rate just means the amount per second. Or we can also look at power as the work done per unit time. And we always measure energy and work done in joules. If we measure time in seconds, this then gives us a power measured in the watt. Now when we think about an energy transfer process, although some of the energy might be transferred to a useful store at the end, some of the energy might also be wasted. Perhaps it's going to heat up the surroundings. And what we can then think about is something called efficiency. And efficiency is often given a number between 0 and 1, or between 0 and 100%. And we can work out the efficiency by looking at the useful output energy transfer divided by the total input energy transfer. Effectively, the more energy that's transferred usefully, the higher the efficiency. And we can do the same thing where we're maybe not thinking about the energy transfer, but the power, and we can look at the useful power output compared to the total power input. We can also look at the electrical power. So this is the amount of energy transferred per second. And what we can say is that the power is equal to the potential difference times the current. Now again, we measure our potential difference, V, in volts, our current in amps, and we measure our power in watts. That's the amount of joules per second that are transferred. So effectively, if you've got a component with a bigger current flowing through it and a bigger potential difference, it's going to transfer more energy per second. But sometimes we might not know the potential difference. And the other equation we can use is P is equal to I squared R. So we can also work out the power, capital P, is equal to the current squared times the resistance. Now again, you've got to remember that energy is going to be equal to power times time. And another way of looking at the energy transferred is equal to QV. So this is Q, which is a charge in coulombs, potential difference in volts, and this then gives our energy transferred in joules. So there's a whole load of different equations that you need to be familiar with that you can then apply to circuits. Now so far we've been looking at direct current, which flows one way around a circuit, but then there's another type of circuit which uses alternating current. This is the kind of thing that you might have in a household appliance where you plug something into the mains. And the UK mains is 230 volts, and it's got a frequency which means there's 50 cycles per second. If we were to look at this on a graph, this means that sometimes you've got a positive value and sometimes it's negative. And this means that the current flows one way, then the other, then the other way, then the other, then the other, then the other, really, really quickly. Now, this is used in normal kind of household appliances. And what we often have is this 3-core cable. So we have 3 different wires in the core of that cable. So the brown wire provides the alternating potential difference from the supply. The neutral wire completes the circuit, and it's the difference between the potential difference here that causes effectively that current to flow. And then finally you've got this green and yellow wire, which is called the earth wire. And this is a safety wire that means if there's a fault in the system, this carries any electricity back to the earth rather than going through your body, as it says over here. So you need to remember some of these facts about an alternating supply, especially the household supply that we have in the UK. Now the other thing that means that AC is really useful is it allows us to transfer energy over large distances, or transfer electricity over large distances, by using the national grid. Now, where can I put this? Just down here. So the national grid is a system of cables and transformers that link power stations to consumers. And what you have in a transformer is you have two coils of wire, the primary and the secondary, and these are wrapped around an iron core. Now, when you have an alternating supply in one, it causes there to be an alternating supply in the other. And this allows us to massively increase the potential difference, but also decrease the current. And this reduces energy losses in our power supply. So you need to know a bit about the national grid and how we have step-up transformers, which increase the voltage, or we also have step-down transformers, which decrease the voltage. So this video is revision of the particle model, which is something that we use in physics to explain the world around us. Now, the first thing we're going to consider is something called density. Now, density is basically a measure of how much stuff there is in a given volume. So perhaps we have two things which have the same volume. So I'm just going to take this off. What we have is the same volume of material here, but this one here is a lot heavier. It's got a bigger mass, and that means that there's effectively more stuff in the same space. Now, the way that we work out density, we use the symbol rho, so RHO. This is a Greek letter that we use to represent density, and it's equal to the mass divided by the volume. Now, because we always measure mass in kilograms and we tend to measure volume in cubic meters, this then gives our density in kilograms per cubic meter. Although sometimes if we were to measure our mass in grams or volume in cubic centimetres, we could also, depending what we're measuring our quantities in, we could maybe look at the grams per cubic centimetre. Now, this particle model allows us to look at solids, liquids and gases. And if we think about the behaviour of the individual particles or molecules, this explains why certain things have certain properties. So I'm just going to consider solids, liquids and gases. So in a solid, we have this close packed regular arrangement of particles. Now they're still jiggling around, they're still vibrating, but they're not really able to move around that material. So that's why a solid is what it is. A liquid, on the other hand, the particles are still really densely packed together, probably a similar density to in a solid, but here they're able to move past each other. And what we have is this random motion of all the particles in a liquid. In a gas, on the other hand, the particles are really spread quite a long way away. They're moving quickly in all random directions, and because of this, we can do things like we can compress a gas or whatever. So let's think about how we go from one state to another. Now, if you have a solid and you heat it up, it turns into a liquid, so that's when it's melting. The liquid then might boil and turn into a gas, but if we have something which is evaporating, this is where something turns from a liquid to a gas below its boiling temperature. This is the reason that things like puddles do dry up. Even though it never gets to above 100 degrees, that water still turns into the water vapour. Going the other way, we have gas that condenses to a liquid, and then the liquid freezes to a solid. But what we also have sometimes is a solid that turns directly into a gas. You might have seen this with some carbon dioxide pellets, and this is what we call subliming. And the key thing to remember is when we move from one state to another, there's no chemical reactions happening, it's just a physical change, which means it can be reversed and they can go back to the state they were in before. Now, I said that all of these particles may be moving around and so on, and what we can then consider is something's internal energy. Now, internal energy is defined as the total kinetic and potential energies of all the particles that make up that system. So this is a combination of their potential energy, which is due to the arrangement of the particles, as well as how quickly they're vibrating and moving around. Now, if we were to look at the internal energy, so this is what this E stands for here, and we look at how that compares to the temperature, what we find is that as you increase the internal energy, the temperature also increases until we get to this point where we have a change of state. And what we find is that when something changes state, so maybe it's, in this case, the temperature is increasing, so it might be melting, it might be boiling, we have that happening at a constant temperature. Now, what we can think about are the amount, or is the amount of energy that it needs to go from one temperature to another. And what we have here, when we have these regions here, we have something which is maybe a gas, a liquid or a solid. If we want to look at the amount of energy that it takes to heat something up, we can then look at something called the specific heat capacity. So the link between the internal energy and the temperature is that the change in internal energy is equal to mc delta theta. where what we have is our change in energy in joules. We've got our change in temperature, that's all the delta means, a change in degrees Celsius. We have our mass in kilograms, and this thing here, C, is our specific heat capacity, and that's measured in joules per kilogram per degree. But what happens when something is changing state? Here the temperature doesn't change, and there we need to think about something called the specific latent heat. And this is then defined as the amount of energy required to change the state of 1 kilogram of the substance with no change in temperature. So this is where we're looking at this region on the graph, or this one up here. And the equation that we can use for this is that E is equal to mL. Once again, we measure our energy in joules, our mass in kilograms, and that means the units for this latent heat, the specific latent heat, are equal to the amount of joules per kilogram. So in this experiment, we're going to be looking at thermal insulation. So what I have is a beaker, which I can put some water in. I've got a thermometer, so I can record the temperature at regular time intervals. And I've got a lid here just made out of a piece of cardboard, and that not only holds the thermometer in place, but it stops any heat escaping from the top. Because what we're going to investigate is the insulation around the side of this beaker. Now I'm actually going to use for this some bubble wrap, because not only does it make a great sound when you're popping it, but it also traps all of these small air pockets. And what we can easily do is we can vary the thickness of bubble wrap that's actually wrapped around this beaker. So I've got a stopwatch here so we can record the time, and also a measuring cylinder, so every time I put some hot water into this, I've got exactly the same volume. And it's better to record the volume on the measuring cylinder because that's a lot more accurate than just pouring it straight into the beaker. So what I'm going to do is, first of all, I'm going to just use the beaker on its own. I'm going to get some water which I've boiled in the kettle, I'm going to put it in, and then I'm going to start the timer, and I'm going to leave it on for 15 minutes, and we're going to record the temperature every 3 minutes. Now there's another way you can actually do this experiment where you alter the different type of insulation material, so you could be using wool or bits of newspaper, but for this experiment and this setup, what I'm going to be doing is varying the thickness of the insulation. So now this is at 80, I'm going to start the timer. So now we've done it with no insulation, I'm just going to take this out. And what I'm now going to do is just very carefully move this beaker, because it is still full of hot water. I'm going to put 2 layers of bubble wrap around the container, and then we're going to repeat the same thing again. So again, we're going to put some hot water in, exactly the same volume measured with my measuring cylinder. And when the temperature starts at 80 degrees, I'm going to start the timer. We're going to take recordings every 3 minutes for the next 15 minutes. But this time we're going to have 2 layers of bubble wrap. And all I'm going to do is I'm going to wrap it around 2 times. I'm going to secure it with a small piece of sellotape. And then we're going to do 4 layers, 6 layers and 8 layers. So we had our beaker with a different number of layers of bubble wrap around the outside, and this is the data that I took, so quite a lot of data there. I took all of my values to the nearest whole number that I could actually read on the thermometer, and when I looked back at the video I found that I think it was closer to 81 at 0 seconds when we had just the beaker on its own. So I've used my value of 81, the other ones I think were all at 80. And then I think, these are my judgment calls about which number I thought it was closest to, but yours might be very slightly different. So we can see, just by looking at the table, that when we had no layers, we had quite a high temperature drop. As we had more layers of insulation, we had less temperature drop, and that's because it was better insulated. So what we can do with this data here is we can plot it on one graph. We're going to have time along the bottom and temperature on the y-axis. So time in minutes over here, temperature in degrees up here. So what I can start to do is to plot some of this data. So at 0 minutes we had 81 degrees. So we're just going to go for 0 layers at the moment. After 3 minutes the value was 76. And finally 63. So this is a set of data, and we can see that it doesn't really fit a straight line, so it's going to be a curved line of best fit. We can actually see we have a steeper gradient initially, so we have a greater rate of temperature loss when we've got a hotter temperature. Now, to put in my line of best fit, I'm just going to move the graph paper over here, and that means I can do a sweeping motion with my hand. So I'm just going to kind of maybe practice that a couple of times. We're going to be looking at something like this. And then you've just got to commit to it like this. Okay, so that is my first line. And I'm just going to label this as 0 layers. Now we're not joining the dots, we're not going to every single point, but what we're looking at is the trend in that data. So I can now do the same for when we had 2 layers of insulation. So now we're going to start at 80 degrees. We then go to 77. And we can now see all of the points are higher because when we've got more insulation, there's going to be less thermal transfer to the surroundings. So again, I'm going to put the graph paper over here and just think about an appropriate line of best fit, something a bit like this. Okay, not having a great attempt at this. If we go something a bit like this. There we go. So I've now got my second line of best fit, and we can see that this is all higher up. So now I'm going to label this as 2 layers. So that's 2 layers. I'm just going to now plot the rest of the data on this graph. So this is what I've ended up with. I've made quite a few mistakes actually trying to put in my lines of best fit. So I've used a rubber to kind of have another go at that. The data for 6 and 8 layers was actually the same. So it seems that as you add more than 6 layers of insulation around the sides, that doesn't really affect the rate of thermal transfer. But we can definitely see the effect of adding 2 layers is quite significant, and then the more layers, it's not really that changing the amount of thermal transfer a huge amount. So that was the data that I took for that graph, and it's pretty straightforward that if you add more layers of thermal insulation around the outside, it's going to keep the water inside hotter for longer. And if we wanted to increase that insulation, we maybe have to think about putting something underneath it and even more layers on top for that lid. So that is my data for the thermal insulators practical for GCSE Physics. So in this video today, we're going to be measuring the density of some objects. We have a regular object, we have an irregular object, and also we have a liquid. Now, if you had a cuboid, a shape like this, you could just measure the length, the width, and the height to work out its volume. But for this practical, I'm going to be measuring the volume of this cylinder over here. And to do that, and actually work out the density, I've got this whole tray of equipment. So I have a mass balance, I've got various other things to work out volumes and dimensions. So first of all, let's start with this piece of wood. Now, in order to measure the mass, I'm going to be using a mass balance. And when I set this up, I'm just going to turn it on. And what I'm then going to do is I'm just going to zero it so it says 0 to begin with. So 0.0 grams at the moment. And if I just simply place this on top, this gives a reading of 26.2 grams. And what we can then do is we can convert that into kilograms. So we've got the mass. Now, to work out the volume, we need to know a couple of things. We need to know how long it is and also the diameter. And if we know the diameter, we can then use the equation pi r squared to work out the area, the cross-sectional area of this cylinder. So to measure the length, I have a ruler. This one here, although it's a meter ruler, it still measures to the nearest millimeter, which is going to be perfect. So I'm just going to hold this to the side, and then you can make a reading very carefully of what you think the length of that cylinder is. And although it's measured in centimetres here, we can then convert that into metres. So we've got the length. Now, to work out the diameter, it's actually quite difficult. If you've got a ruler and you're trying to put it to the side, it's very difficult to get a good reading. So what I'm going to be using instead is this device over here. So this is a digital caliper, sometimes called a micrometer. And what we can do is we can use the jaws here to measure the width or diameter of something like this cylinder. So it's turned on. The first thing I'm going to do though, is I'm just going to gently close the jaws like this, and I'm going to press 0. So we know that we've reset this. If I then open it, I'm going to clamp this on like that. And again, I'm just doing it gently, so I'm not actually compressing that wood. So the first measurement is 23.31 millimeters. 23.31. I'm going to do it again in a different place so we can actually check it's cylindrical and circular all the way around. So 23.14. And I'm going to do it finally one more time. Let's just go here. And I've got 23.47. So now we have 3 different values for the diameter. We can calculate the mean. We can make sure that we've converted this into meters. And now we know the diameter and the length, we can work out the volume. And as we know the mass, we can now work out the density of this regular shape. Now the next thing we're going to look at is this polystyrene. Now it's not a regular shape, and you can see that if we were to use even things like this micrometer here, it would be very hard to take the measurements to calculate the volume. So to work out the volume of this, I'm going to be using a different method. Again, first of all, I'm going to put the mass balance here. I'm going to 0 that, and I'm just going to put this on top. So that's 0.4 of a gram, so it's very, very light. Now to work out the volume, what I'm going to be doing is using a displacement can. Sometimes it's called a Eureka can, and what we can do in this is we put some water into it, and then when we put this object under the water, it displaces water equal to the volume of this. So to do that, I have a box over here. I'm going to put it on top of the box. You could of course do it over the edge of the desk or near a sink. And what I'm going to do as well is just pour in some water into this right up until we get to the spout. And then this other beaker is just going to catch any excess that comes out. So there we go. Good. Now, in order to actually measure the volume, we're going to be using a measuring cylinder. Now these do come in different volumes, and we want to choose one which is appropriate for the volume that we're testing. I think that this one here is going to be good. So this is a 25 milliliter measuring cylinder. And when I put this in, what you'll notice is that hardly any water comes out because this polystyrene is actually lighter than the water. So in order to submerge it fully, I could just put my finger in, but then I might have my finger underwater as well. So what I'm going to do is try using a paper clip. So I'm just going to bend a paper clip, and what I can then do is use this to push this underwater and catch the water that comes out. So there we go. And in order to actually measure the volume of water here, what I'm going to do is I'm going to make sure that when I put it down, I'm going to look at eye level to take the reading. And we're going to be looking at the bottom level of that water. And this is what you might be doing and quite familiar with doing in chemistry as well. So what we can now do is we get our eye level to this, and we can record the volume in millilitres. And don't forget, of course, that 1 milliliter is the same as 1 centimetre cubed. And we can then convert that into cubic meters when it comes to working out our density. So that one was polystyrene. And the final density is for a liquid. This liquid here is actually sugary water. So I've dissolved a lot of sugar into this water. And in order to work out the density, again, we need to know a mass and a volume. I'm going to use, again, my mass balance here. I'm going to choose a large measuring cylinder. And what I'm going to do is put it on top and then 0 this once again. So what I can then do is add some water. It doesn't really matter exactly how much. So we've got 252.2 grams of sugary water. We can actually record the volume by keeping our eye level by the side of the measuring cylinder. And now we can use the formula that says the density is equal to the mass divided by the volume. We can do that for the wood, for the polystyrene, and also for this sugary water. And in the next video, I'm going to go through the results that I took. So these are the results that we took when we looked at the density of different objects. And now what we're going to be doing is developing our math skills, where we're going to be looking at calculating the volume of a cylinder. And then we're going to be doing some unit conversion and maybe using standard form as well. So the first thing we're going to do is we're going to look at the average value for the diameters. And here I've got my values that I recorded from that last video. And all of them are times 10 to the minus 3 because we're going from millimeters to meters. So to work out the average, it's going to be 23.31 plus 23.14 plus 23.47 divided by 3 to give an average value of 23.31 millimeters, which is therefore 23.31 times 10 to the minus 3 meters. Okay, now when it comes to working out the volume of a cylinder, it's going to be equal to the cross-sectional area, which is pi r squared, times the height of that cylinder, or in this case the length. So it's pi r squared L. So that's going to be pi multiplied by the radius. Now up here we have the diameter, so the radius is going to be equal to 23.31 times 10 to the minus 3 divided by 2, because we've got half the diameter is the radius. That's going to be squared, and then we're going to multiply that by the length, which is 0.098 of a metre. So to work this out, we're going to do 23.31 times 10 to the minus 3. We're going to divide that by 2. We're going to square that, and we're going to multiply this value by pi times 0.98, which gives me a value of 0.0000418. So that's equal to 4.18 times 10 to the 10 to the minus 5 meters cubed. Now to work out the density is equal to the mass divided by the volume. So here the density is going to be equal to the mass over the volume, which was 0.0262 kilograms, divided by this value here, 4.18 times 10 to the minus 5. So I'm going to leave this value in my calculator, and I'm going to do 0.0262 divided by this answer, which equals 626.47, which is 630 kilograms per cubic metre. So kgm3. So 630 kilograms per cubic metre is the density of wood, and that's actually kind of what we'd expect. It's going to be less than 1,000, which is the density of water, and that means wood is less dense than water, so it floats. So that's the first one, quite involved mathematics. Now for the second one, the first thing I'm going to do is convert this volume from millilitres into cubic metres. Now it says down here that 1 millilitre is 1 centimetre cubed, which is 0.000001 metres cubed, which is also the same as saying 1.0 times 10 to the minus 6 cubic metres. So this value here is also 21 times 10 to the minus 6 cubic metres, which could also be written as 2.1 times 10 to the minus 5. So when it comes to working out the density, that's equal to the mass divided by the volume, which is 0.0004 divided by 2.1 times 10 to the minus 5. So a small number divided by a really small number. And this gives a value equal to 19 kilograms per cubic metre. So we can see the density of polystyrene is a lot less than wood, as we'd expect, and pretty much floated on the water. And finally, we've got the sugary water. Again, the volume is 230 millilitres, so that's 230 times 10 to the minus 6 cubic metres, which is 2.30 times 10 to the minus 4. And again, density is going to be this mass divided by that volume, so 0.2522 divided by 2.30 times 10 to the minus 4. And then again, if I just use my calculator, this gives a value of 1096.5. So to three significant figures, that would be 1,100 kilograms per cubic metre. which again is kind of what we'd expect. Because it's got the sugar dissolved in it, it's going to have a slightly higher density than normal water. So this one here is 1,100 kilograms per cubic metre.